So how we figure out whether hyperconjugation is present or not? The requirement for hyperconjugation is presence of alpha hydrogens. What are alpha hydrogens? The hydrogen atoms present at adjacent carbon to a positive carbon, to a free radical or a double bonded carbon. The carbon adjacent to a positive carbon, free radical or a double bonded carbon is known as alpha carbon, and the hydrogens present on that is known as alpha hydrogens. More is the number of alpha hydrogens, more will be hyperconjugations. The number of hyperconjugating structures, the number of hyperconjugating structures, how many a given species will have, can be calculated from the number of alpha hydrogens. For example, if I ask you how many hyperconjugating structures will this species will have, you can easily say the number of alpha hydrogens over here is 3. So the number of hyperconjugating structures this species will have 3. Similarly, if I take the number of hyperconjugating structures for a species like this, if I take something like this and I have a positive over here, so how many alpha hydrogens does it have? This carbon is alpha, this is alpha, this is alpha. Alright. So how many hydrogens are present on this carbon? This carbon has one bond over here. So each carbon has 4 bonds. So one bond is over here. So the remaining bonds are 3. So 3 bonds are attached to hydrogens. So this is CH3. Here you can see it is CH2. This is CH2. So the number of alpha hydrogens is 3 plus 2 plus 2. 2 over here, 2 over here, 3 over here. So in totality, the number of alpha hydrogen is 4 plus 3, that is 7. So number of hyperconjugating structures equals to 3. 3 in the top case and 7 in this case, because number of alpha H was 7. Similarly, you can figure out in a given species number of hyperconjugating structures by counting alpha hydrogens. More is alpha hydrogen, more is hyperconjugation, more are hyperconjugating structures. So this is a very easiest trick you can apply whenever you are required to find out number of hyperconjugating structures. Stability of a carbocation, stability of a free radical and stability of alkenes is directly proportional to number of alpha H. Stability of carbocation, free radical and alkenes is proportional to number of alpha H, because more is alpha H, more will be hyperconjugation and more will be stability. For example, we have taken few examples over here. So this is alkene and here you can count number of alpha hydrogens. This is alpha carbon, in this is alpha carbon, here you have 2 alpha carbons. So you have to count all alpha hydrogens. Alright, over here 3 alpha hydrogens are present. Alright, so number of hyperconjugating structures has to be 3. Here the number of hyperconjugating structures is 3. Here the number of alpha H is 3 plus 3 is 6. So number of hyperconjugating structures is 6. Here you have 3 plus 3 plus 3, 9 hyperconjugating structures, because number of alpha H is 9. Alright. Similarly, next we are going to study about homolytic fission. What is homolytic fission? When we have a bond like this, and it breaks in a way that it one electron goes this way, one electron goes this way. What you will have, 2 carbons each having one odd electron. So these are known as free radicals. The species having odd electrons is known as free radicals. They have odd electrons, so they are also paramagnetic in nature. So free radicals are born out of homolytic cleavage. Homolytic cleavage gives rise to free radicals. They are neutral species where they have unpaired electron on the atom. Alright, so this is it. Thank you.